How can you visualize particle swarm optimization? Have you ever wondered how a swarm of tiny particles can work together to find the best solution to a problem? This is where particle swarm optimization comes in. It's a fascinating algorithm inspired by the way birds flock or fish swim together. Visualizing this process can really help us understand how it works, especially in fields like robotics and automation. To visualize particle swarm optimization, we can start with simple two-dimensional and three-dimensional position plots. Imagine plotting each particle's position as it moves through a search space. In two-dimensional problems, you can see points moving across a graph. For three-dimensional problems, it gets even more interesting as you can visualize the particles in a 3D space. Adding contour plots or surface plots of the objective function can show how these particles navigate through peaks and valleys in the search landscape. Animations can take this a step further. By creating a dynamic visual, you can watch how the swarm behaves over time. Tools like PySwarms offer built-in functions for these types of visualizations, allowing you to see particle trajectories and how they converge toward the best solutions. Another effective way to visualize particle swarm optimization is by tracking the best positions. Each particle has its personal best position, and the swarm has a global best position. Highlighting these points on your plot can show the guiding forces behind particle movement. Using distinct markers or colors can make these best positions stand out, making it easier to understand the optimization process. Heatmaps and density plots are also useful. They can representing where particles are concentrated in the search space. This is especially helpful in multi-objective or high-dimensional problems, where direct plotting of positions can be challenging. For high-dimensional optimization problems, we can use dimensionality reduction techniques. These methods help map high-dimensional particle positions to two-dimensional or three-dimensional spaces while keeping relative distances intact. This allows us to visualize swarm behavior without losing important information. There are specialized visualization tools designed specifically for particle swarm optimization. For instance, SwarmViz is an open-source tool that lets users set up experiments on benchmark functions or real data, such as robotic controller parameters. This tool offers interactive graphics to visualize the optimization process, making it easier to monitor swarm progress and understand dynamics in robotics and automation. Lastly, application-specific visualizations can be created. In swarm robotics, for example, you might visualize how particle positions relate to robot controller parameters or behaviors. This can show how optimization improves robotic performance in real-world scenarios. In summary, visualizing particle swarm optimization involves plotting particle positions and trajectories, often combined with function landscapes and animations. For high-dimensional problems, dimensionality reduction and specialized tools can improve interpretability. These visualizations are essential for understanding and improving particle swarm optimization, especially in the exciting fields of robotics and automation technologies.